so Dan mentioned that one of the things he was interested in is having some really nice way to describe contextuality in a whole bunch of general scenarios in relation to Wigner functions. And what this talk is about is coming up with some really nice, clean condition for this kind of GHZ, or we call Mermin non-locality, in a very, very large class of examples. And so we're basically going to hit this with the sledgehammer of abstraction and come down with a really nice, clean condition. So the framework, we talk about these two ideas in the title, abstract process theories. We think about quantum mechanics as an example of them. It lives in the category of finite dimensional Hilbert spaces and linear maps. And then we can extract up to abstract process theories, which are any dagger symmetric in order category. F-held is an example of this. So that's what those are. I'll talk more about in a second. Mermin non-locality, we should remember from Dan's talk the last couple of days, or just in general. That's some GHZ state, we do some measurements. And we've got a whole bunch of different sets of those measurements. Now this is an example of what's called a 3-2-2 Mermin non-locality example. So this is three systems, with three-point GHZ state, two choices of measurement, x and y, each of which have two outcomes. So this work is building off of something that Dan mentioned, this book work by Bob Cook, Bill Edwards, and Rob Speckens in QPL 2009, where they analyze Speckens' toy theory in relation to Mermin non-locality in this qubit and Speckens qubit case. And then also work by these other authors that look at it more generally, but focus on Hill. So this, I would like to be able to explain this entire framework, which is also sometimes called generalized compositional theories. But we're sticking with process theories, right? So if you want to learn more about just that general framework, there's a nice summary article that's recently been put on the archive. So here's the headline. So we're going to give full and sufficient conditions for some abstract process theory to have a Mermin non-locality argument. And this is going to be the same as there being some algebraic condition on these things called phases. And we'll explain exactly what that is. Now this is going to apply for Mermin non-locality arguments of any number of parties, where they make any number of different kinds of measurements, which can have any number of different outcomes in any abstract process theory. So that's the sledgehammer of abstraction. And so in particular, when you then reflect back on application just to quantum theory, we'll also connect it to, it's connected to quantum security protocols and some other stuff. So Mermin measurements. So first we need to define these things called dagger Frobenius algebras. So they're a Frobenius algebra where there's some monoid and some comonoid. This is the multiplication in the unit, co-multiplication in the co-unit. And we can say that these Frobenius algebras are quasi-special if they obey this equation. So I'm going to read my diagram from bottom to top, and this is like composition of maps. So this is the comonoid composed with the monoid on top is equal to the identity times some scalar. And and they can also be commutative. So when these monoids and comonoids are commutative, we call them commutative dagger Frobenius algebras. So we can think of these as generalized orthogonal bases when we lift them up from F over to abstract process theories. So now we can also talk about complementary bases. So that would be complementary or strongly complementary dagger quasi-special commutative Frobenius algebras. They satisfy this thing called Hopf law, and they form a unscaled bialgebra equation. So you should have seen these in the talks by Pavel in a slightly different context and also sideways. Oh, I should say something about this. So the difference, so complementarity, there's this Hopf law thing, ends up corresponding in F to mutually unbiased bases. Strong complementarity, which is the addition of this bialgebra law, has something to do with the existence of a Fourier transform over finite groups in a very, very general setting. And there's another paper between me and Stefano on that. Right, so if you've got one of these generalized bases, we'll draw them with different colors, right? The green one is one basis, the red one is another basis. So if we've got one of these generalized bases, then the set of classical points, or also called copyable states, are states which are copied by the comonoid, or also just completely deleted and ignored by the co-unit. And in some sense, a motivating intuition is to think of these as the basis elements, though they don't always obey in abstract theories everything that a basis does in Hill. So now I'm going to introduce two kinds of groups. One is a group over the classical points, and the other is this phase group. And these are the key structures for the main results in this talk. So if you've got a pair of strongly complementary generalized bases, dagger quasi-special commutative algebras, then the monoid of one, the green one, acts as a group on the set of classical points of the other. And there's some kind of anticode. And for those of you that kind of know a little bit of, which is a lot of people in this room, know a little bit of this, there's a quick way to show this with the hop flaw. So if we have two elements which are classical points of the red dot, G, then with this little anticode thing in here, we pull them through via copyability. We apply the hop flaw, and then this is again a classical state rule, and it's easy to see that G with the antipode is the inverse of G. You can read that survey paper to understand what's going on. Okay, so that's the first group. That's a group of classical points on the red basis. The other group is this thing called a phase group. So now we're going to look at the green basis. So if we've got some dagger quasi-special commutative algebra, then the phases are states which obey this law. And we can also make a map out of each state via this definition. So it's also true, so just like how we saw that the green monoid acts as a group on the classical points of red, it also acts as a group on the phases of the green structure. And it turns out that the classical points one is a subgroup of the phase group when these two are strongly complementary. So these are just general results from the literature that apply in abstract groups. Great. So we can look at GHZ states. So if we want to prepare a GHZ state in the green basis, so this is like saying we're picking the green basis as our computational basis. Then for n systems, it ends up being this map, and which actually should be capital N. Sorry about that. And then, so this is, I don't quite have time to explain why this is, but we can think about measurements in this basis as a sort of doubled map. And the reason I want to throw these things up as examples, and you can see this reference for more information about this, is that if we think about this as a measurement in the x basis, remember this is our computational one green, then we can create some other measurement by applying some process before doing the x measurement. And in this case, this is like applying a unitary before a measurement. And in fact, it's like applying a phase gate before the measurement. So this ends up being some other kind of y alpha indexed by whatever phase gate we apply before doing the x measurement. So the takeaway is basically we can represent different kinds of measurements by using phases before applying some chosen x measurement. Right, so Mermin scenarios are you compare some kind of GHZ and then you do like 3 sets of x measurements on the different n parties that you have, 3 parties. So in general, it looks like this. This is a double GHZ state, so you have some GHZ state, and then you do some kind of measurement on top. And so here we've chosen arbitrary phases that are applied for some x measurement, which is like saying we have a lot of arbitrary freedom in what the measurements are going to be. So we're going to call one of these Mermin measurement, so that's like just one of the triple x's. And then we're going to call a Mermin measurement scenario a whole set of these guys, where we make different settings for the measurements, which is like making different settings for the alphas. So one Mermin measurement scenario, like XXX, would be to set all of these alphas to 0. So then they're all x measurements. And then to create a set of those, we pick a set of phases that go into each Mermin measurement to get a scenario. Great. So from these, the setup, we can try and drive some kind of contradiction. So if we're going to have a contradiction, we need to contradict against something. So we're going to contradict against some local equivalence. So if we have some Mermin measurement scenario, this looks a little bit scary as a diagram, but it's actually really easy to explain. So what you'd want a local theory to do is to just assign fixed outcomes for each different measurement, regardless of the other measurements that happen in its context. Right? So we've sort of rearranged things here. So here we have all of the phases for the first, let's say this is triple x, the first measurement context. So this is measurement context 1, and we have a set of these measurement contexts all the way from 1 to s. So for each alpha corresponds to a different measurement. So in the cubic case, alpha of 0 is x, and alpha of pi over 2 is y. So what we want is on each system, we have some fixed value for each alpha. Like in system 1, we have some fixed value for alpha 1, all the way through to alpha m, and we just want to connect it up in the right way that we'd expect it to connect up. So if this is 0, then we want, if we set this to be to be 0, then we want it to go to everywhere that alpha 1 equals 0 appears. So every x measurement for system 1 should be connected to this dot. And that's what this kind of rule says. So then if there's a local hidden variable model, it means we can replace our quantum GHZ with phases and measurement thing with the construction of some fixed state of measurement values for each alpha and some local map. So the way it's presented here is, so we will quantify over all the different measurement setups, so different measurement contexts. And for each measurement context, we can replace the outcomes with some fixed local hidden variable. Questions? Quick? Good. All right. So we can now use this to say something generally about the categories. So if we've got some dagger spectrum of the categories, some abstract process theory, we'll say that it's Mermin local if all the possible Mermin measurement scenarios, any party, any number of measurements, any number of measurement outcomes, admits a local hidden variable model in this definition. It's Mermin non-local if there exists just one or many more Mermin measurement scenario which cannot be represented by one of these local maps, which we've anticipated to be. Great. Okay. So now in the next section, I'm going to show that these conditions can be checked by some nice algebraic condition on the phase groups and the classical point group that I introduced in the beginning. So I'll introduce this thing called non-trivial algebraic extensions. It's about groups, so let's look at two groups. Let's look at this additive group G, which is some abelian group, and it actually doesn't have to. Anyway, we'll call it abelian for now, and some subgroup H. So we'll say that G is a non-trivial algebraic extension of H by introducing a finite system of equations over that group, so with integer-valued equations. So we can put integer coefficient equations. We put some integer coefficients. This is a sum in the group H, let's say, equal to an element of H. So it's probably easy, and if there does not exist, I'll read the whole thing. So it's a non-trivial algebraic extension of H if there's a finite system of equations which has solutions in G but not solutions in H. And it's trivial if switching from H to G doesn't let you solve any more equations. Best to illustrate this with an example. So let's look at a really simple example. Multiplicative in this case groups. So we'll look at the finite abelian group +1, -1, plus I, minus I with multiplication of 1. And then this simple subgroup of plus or minus 1. So here's an example of an equation which has a solution in G but no solution in H. So this is a multiplicative group, so the coefficient is an exponent. So this is an example where G is a non-trivial algebraic extension of H. So here, we only have one equation in the system, but in general, we can have a system of equations. Does this example make sense? Before I move on, any questions? Yeah? So one nice general structural feature of these trivial and non-trivial algebraic extensions is if G has two factors, K and K prime, and H is one of them, then every system of equations will have some solution in G only if it has one in H. So if you have this setup where H is a factor of G, then it's going to be a trivial algebraic extension. So if we've got, now let's return that back to our abstract process theories framework. So if we've got some pair of strongly complementary bases, then we're going to say that the generalized bases, then we're going to say that the pair has algebraically non-trivial phases if the phase group is a non-trivial algebraic extension of the classical points. So remember, if we've got some strongly complementary bases, we're guaranteed to have the classical points be a subgroup of the phase group. That's true always. So now we just ask whether or not the phase group is an algebraically non-trivial extension of this subgroup. So, quick examples. So in the ZX calculus, or equivalently in qubits in FHIL, we have the phase group is isomorphic to Z4, and the classical points are isomorphic to Z2. So that means the phase group is a non-trivial algebraic extension. On the other hand, if you look at the abstract process theory for Spekens toy theory, then the phase group is Z2 cross Z2, and the classical points are Z2, which is a trivial algebraic extension, because this is a factor. Great, so our results that we use with these things is, if we start with some process theory, diagonal category, maybe quantum, and we've got two strongly complementary dagger, special quality, special computer for Phoenix algebras, generalized basis. And we suppose further that the classical points are, and in this case, a basis. So this is like up to, we add a little bit more conditions on these classical points to be more basis-like, this sort of asterisk. Then if the phase group is a non-trivial algebraic extension of this classical point subgroup, then you can always make a Mermin non-locality argument, and actually we can show you how to construct that, not in the talk. So this immediately means that we can see that the ZX calculus is going to be Mermin non-local, because as I said, this is a non-trivial algebraic extension. Further, if the phase group is a trivial algebraic extension, then it's Mermin local. That means there does not exist any non-locality argument for, again, all that arbitrary size and shapes. And an instance of this is exactly what is in that this QPL paper, where they show that spec is different from stab. So again, this is a trivial algebraic extension of this one by the sort of factory rule that I mentioned earlier. And now the thing we originally were trying to hit our heads against when we had to like move into this entire area, which is we were trying to look at what happens in REL. So REL is a dagger spectrum we know to category FREL of finite sets and relations. And it turns out that this is Mermin local. And this is because the phase groups are some product of H groups G, and the classical points are a single group G. Now it actually isn't one of the factor groups. It's like the identity of this group is the identity it's a vector of the identity in one of each of these factors, but this is still a trivial algebraic extension of the classical points of this. And then, and there's a whole bunch of talks actually this week about REL as a model for quantum theory. So it makes a very, very interesting model in many ways. And one of those ways is that it's actually it's a Mermin local model, but it still has all these interesting properties that relate with quantum theory. Great, so I'll tell you a couple of the concepts that we use in the proof. Don't worry, nothing too crazily detailed. But if you've seen the diagrams before, it might be nice to see how this works. So the n prototype Mermin measurement I mentioned before by some simple, strong complementarity rearrangements that are actually in this original paper by Alex and Bob Ross. You can rewrite this. So we see we've got a sum of phases here. Now what we want to do is just introduce some integer coefficients, because you could have repetitions of the same phase. So we're just going to introduce them like this. And then we set the total sum equal to sum A, and we just ask if we can find some phases that will satisfy this equation. And we'll do that for every single Mermin measurement, and that will give us our Mermin measurement set of scenarios. One of the key things that goes into the proof of the actual locality and non-locality relation is that this A that comes out at the end needs to be a classical point. So that's one of the key requirements. Great, and the other way around is really nice, which is that every time we make one of those sets of equations, we can also associate it to a Mermin measurement scenario. So then in the paper, which I won't go into now, this is connected to the existence of one of those local maps in the way that I described it earlier. So if you have a local hidden variable model for a Mermin measurement scenario, then it's equivalent to a solution in classical points for that associated system of equations. And if all of one of these in the system of equations has a solution, then there's a local hidden variable model. And if some points, so if we can find some set that doesn't have some set of equations that doesn't have a solution, then that means you can directly construct some non-locality proof by using the coefficients and the phases to become the phases in your measurements. Okay, so what do we use this for? So one thing that's really nice and that one can connect it to, if they have a lot more time, is that these Mermin non-locality protocols look a whole bunch like quantum secret sharing protocols. And so our characterization links, so anyway, it turns out that whether or not there is a local map is the same as having a secure or not secure quantum secret sharing protocol. And this sort of comes down to the fact that if you have some local hidden variable, then the local hidden variable can be manipulated. So by having some really big characterization of any number of parties, any number of measurements, any number of outcomes, Mermin non-locality, you've got the same generality for quantum secret sharing setups, which is really nice.
Well, what's H for me?
It's there. It's a particular. It's in the. Yeah. It's just. Yeah. I can show you it's in the paper. It's a particular setup. Nothing too fancy. So yeah, to reflect on what's kind of already looked at in the literature in terms of generalizations of these Mermin non-locality things. Oh, also, yeah, Vladimir has a good little master's thesis on this connection as well. So there's more there too. So current literature for generalizing the Mermin non-locality argument looks. This is again this kind of like number of measurements. Number of parties, number of measurements, number of dimensions or measurement outcomes, which are the same in Hill, but not in general. And a lot of them really, they focus on these two measurement scenarios, where you have two different measurements, like having x and y. And in this particular case, so when you have qubits, it turns out that your x and y measurements have to be complementary. This is not true at all in general. And in fact, you have a really, really large wealth of options for what your measurements can be. It's, any one of those systems of equations that you can create which doesn't have a solution will give you a huge number of measurement scenarios. And in the paper, we do have some little numerics that show kind of how this grows for Q-trits and stuff like this. So you have a whole bunch of measurement options that are not complementary. So to summarize, we've taken the abstract sledgehammer and presented a full characterization of Mermin non-locality, any number of systems, any number of measurements, any number of outcomes in any process theory. And we've done this by connecting it to an easy-to-check condition on the phase groups and classical groups of these sort of generalized bases. And then we connect with an insight into connection between non-locality and the security of certain quantum protocols. And then, like sort of a simple corollary is that you don't need to worry about having complementary measurements. You can definitely create Mermin non-locality scenarios just like this without complementary measurements. So, thanks a lot.